Hi everyone, my name is Jacob.
And my name is Martin.
And we're here to tell you about some of the ongoing work in extending Enzyme to MLIR for reverse mode gradients. We'll begin with some motivation and some background. For starters, what even is MLIR? Well, it's an acronym that stands for Multi-Level Intermediate Representation. It is a compiler infrastructure and IR that is extensible at its core. It is broadly grouped into dialects, where the different dialects can have their own ops and types at dramatically different abstraction levels. For instance, we have the lineage dialects, where individual ops are high-level linear algebra computations, such as matrix multiplications and convolutions. A bit lower level, we have the SCF, or structured control flow dialect, which contains constructs like if statements and for or while loops. At the lowest level that MLIR goes to, we have the LLVM dialects, which closely maps to LLVM-IR instructions. We have operations like get element pointer. In contrast to SCF, where you would see structured control flow like ifs and loops, at the LLVM dialects level, you would truly have an unstructured control flow graph with branch instructions. We also have the memref dialect. Memrefs are MLIR's representation of shaped regions of memory. They're somewhat analogous to ND arrays in NumPy, and you can do things like allocate them, deallocate them, read from them, write to them, or index into them. And the memref dialect contains operations for all of these and more. And like we said, MLIR is extensible, so it makes it very easy to add new dialects with your own ops, your own types. You can make your ops do whatever you want at whatever abstraction level you want. Now, why would we use MLIR for Enzyme? Well, it is our belief that Enzyme, or more broadly automatic differentiation, and MLIR can have a symbiotic relationship where they are mutually beneficial to each other. We'll go over each of these symbiotic directions in turn. In the first direction, we believe that MLIR would greatly benefit from a unified AD system. For starters, the users of MLIR currently are primarily grouped into machine learning practitioners and high-performance computing people. And all of these people have different needs for automatic differentiation. In ML, the canonical way of training neural nets is through backpropagation. And in HPC, we have a number of people here that have a broad range of need for derivatives. So MLIR is used for more than just tensor DSLs. In particular, the ecosystem has projects like Polygeist, which is an MLIR frontend for C and C++, and FlangNu, which is an MLIR frontend for Fortran. The current landscape is that there is a tendency for AD to be re-implemented for the different applications where it is required. And these implementations often come with different trade-offs and quirks and assumptions about what they will be differentiating and the best cases for each of them. At this point, you might be thinking, OK, so a lot of people that use MLIR need AD. But MLIR can very easily lower to LLVM-IR. Why don't we just do that and then use LLVM Enzyme? And that is that is definitely a valid option, although it comes with some trade-offs. This is the representation of a matrix multiplication using the linear algebra dialect of MLIR. This is the same code in LLVM-IR. There are undoubtedly advantages of performing Autodiff at a low level, such as LLVM-IR, but some of the important trade-offs are that, in general, the code you are working with carries less static information due to it being sacrificed and being lowered to LLVM-IR, and the quantity of code that your AD system must churn through is much larger, on average. I will now hand it over to Martin.
So in MLIR, there are also some more benefits that we can leverage. For example, in most cases, we can assume that the types that MLIR gives us are the types that we also receive, which is not the case in C++, which is why we usually need to do quite costly type analysis. So for example, here you can see that the same mem copy in C++ returns void pointers where we need to do type analysis. And in MLIR, we can just use the memref copy, which gives us the type and which is preserved. And this has the potential to improve compile times significantly, because we retain more information about the IR. Additionally, as Jacob already mentioned, is that we have a lot smaller code size and better information with LLVM than LLVM. Also, it turns out that in most cases, high-level languages are more easily differentiable than low-level languages. And we are also, in most cases, able to apply optimizations more easily on high-level code than on low-level code, such as in the paper presented by Jacob. Additionally, we can also do what the core thesis of Enzyme is that we optimize our code before running AD, but we can also do this on a higher level than in LLVM. And also, Enzyme MLIR makes AD more extensible, since you can add your own dialect and you're not restricted to the instruction set that LLVM provides. So next we are going to continue with the implementation, and our goal with this is to make Enzyme MLIR as dialect agnostic as possible. And in general, we want to do this through interfaces, such that these that transformations are defined by their interfaces. For this, each Enzyme MLIR defines an reverse Autodiff interface for each op that requires a derivative. So for this, we will present how this would go in a primary algorithm, which is in 3 steps. First, for each op, we will need to initialize zero out the shadow memory and the caches for values that we will need later on in the computation. This we will do in 2 functions, one which is cache values, where we cache values which we will need later on in the reverse pass. And we will also have a function create shadow values, where we will potentially create shadow values for the gradients that are created. In the next step, we will have to create the reverse control flow graph for our program, and this can, in general, be done by Enzyme MLIR, completely agnostic of dialect. And then we will, of course, need to create the adjoint, and we will do this in a function called create reverse mode adjoint. And this also supports differentiating child regions of functions. For example, if we have a for operation, we will need to differentiate the region inside the for operation. So in the end, our interface, which will be needed to implement to be implemented for a new dialect, just contains of 3 functions with which we can potentially differentiate most dialects. And we also emit custom operations where we will store the gradient inside, which is the enzyme gradient, where we can get and set the value of it, which abstracts away storing values. And we will also have a cache, which behaves much like a stack, which we can push, pop, and get from. And then the general pattern of a differentiated program looks like this, where we first initialize the storage for the gradient and the cache. Then in the forward pass, we will write our operands which are needed to this cache. And we will, of course, execute our operation. And then in the backward pass, we will, of course, restore the arguments which we will need to compute. Then we will get the gradient for the operation. And, of course, compute the derivative for this operation. And then we will set and add to the gradient for this operation. And next, we will talk about possible optimizations. So, of course, in MLIR, you can start at a high level, but lower down arbitrarily. And this can be done for our codes where you can arbitrarily lower to a certain dialect if that potentially increases your performance. Then we can also, as mentioned before, optimize our code before we run automatic differentiation. And we have also post-automatic differentiation optimizations, which we can decouple from the process of automatic differentiation, since we emit abstract operations which define what AD does, and we can do this agnostic of all dialects. And we preserve the high-level information, since we don't just create a, for example, a memory of load, but we create a enzyme get, which has more semantic information. And we can specifically target them so that all our optimizations work for most dialects. Next, we will continue with a usage example.
All right. So for this usage example, picture this. You have a new language that targets MLIR. You use a new dialect, and your operations do some incredibly new thing. And you want to extend your language with automatic differentiation. How do you do this? Well, we'll take you through a few simple examples of implementations of our interfaces, as well as one trickier example to demonstrate what you need to know as a user. So, quick recap. The key here to make our system dialect agnostic is our interface, which consists of the three methods around storing values that you need in the backward pass, initializing any shadow memory, and synthesizing our differential instructions. We'll take a look at perhaps the simplest case, which is the rf.addf. This is simply a sum of a and b, which are both floating point numbers. The first step is that we think, what is the derivative of our operation? What should we do? We'll make a plan. Mathematically, the derivative of the sum of a and b for both a and b is merely the derivative with respect to r, or the differential value for dr in this case. So first question, do we need to cache anything? And in order to answer that, we look at the expressions for our dA and our dB. Crucially, we see that we don't see any primal values. The expressions for dA and dB do not contain a or b or r. So we can just return an empty vector because we don't need to cache anything. We then look at creating shadow values. The core question to ask yourself here as a user is, does this op interact directly with memory? In the case of an addition, it's only computation, and there's no memory here, so we don't need to worry about any shadows. As a result, our implementation is left empty. Finally, the synthesis. The basic idea here is to synthesize or create instructions that implements the mathematical rule for our simple op. We have this invert function, which kind of abstracts away some of the internals of enzyme MLIR in order to get our differential value of r, and then we emit instructions to plus equals the shadow locations of both dA and dB, or more concretely in MLIR speak, the left-hand side and the right-hand side of our op. We'll now look at a slightly more challenging example that requires one new concept. In this case, we have binary multiplication. And as you can see starting from our mathematical principle of our rule, that we do have dependencies on primal values. The derivative with respect to a depends on the primal value b, and vice versa. So when we implement our cache values method, we must explicitly emit instructions, and this would basically consist of the enzyme init and enzyme push instructions that we saw earlier, and then we return them in a small vector of MLIR values. Again, we aren't directly interfacing with memory, so we don't need to do any special handling of shadow memory. It's just emitted here, but again, it's empty. And just like our add example, we finally synthesize the instructions, which is just a straightforward implementation of our mathematical rule of how we handle our up. Now for memref alloc. How do we need to handle a memory allocation of a memref in our adjoints? Well, intuitively, if you've read the enzyme paper, the first step is that we need shadows such that the shadow is an exact copy of our original buffer allocation that is the same shape and the same type. And actually, I said the first step, but that's the entire process. So we don't need to cache anything because there are no primal values we need to reaccess because the shadow initialization happens at the beginning, so there's no risk of overwriting. Caches can be empty. For the shadow value itself, we do need to implement it, and it's exactly as I described. We just allocate a new memref of the same shape and the same type as our original memref, and then we have this map shadow function, which tells enzyme MLIR that the newly allocated memref is the corresponding shadow of our original memref. And then we're done. And in this case, we don't need to synthesize any differential instructions for special handling. This is it. We'll now look at a slightly trickier example. We'll look at the memref subview op, and we'll, as always, begin with the conceptual understanding of what we're supposed to do. So if you're unfamiliar, the memref subview returns a memref that is explicitly a view of another memref. In this case, we have a starting memref A, which is 2 by 3, and B is the subview, specifically the first column of A. Now, how do we handle this? The crucial thing to remember here is that from an Autodiff perspective, B and A have the same underlying memory. So if one is written from or crucially mutated, the other will also be mutated. We need to make sure that there is a sharing happening here. And that is the key of how we will differentiate our subview op. As we talked about in our allocation, we have a shadow for A, which is a memref of the same shape and same elements type that is initialized to zeros. And then in order to correctly make sure that updates from both B and A get propagated to the same place, the shadow with respect to B is merely a view within the shadow with respect to A. But in other words, the shadow of the subview, which is B with respect to B, is equal to a subview of the shadow with the same offsets and same locations and all of that, which is shadow of B with respect to shadow of A. All right, so now that we have this conceptual understanding of our plan, the implementation that follows is quite straightforward. Again, we don't need to cache anything. We don't need to synthesize anything. And then the handling of our shadow values, which happens as an initial step, is merely creating the corresponding subview that matches our original subview, only it now indexes into our shadow buffer. We'll now go into future work.
OK. Our future work consists mostly of exploring more data flow analysis of in MLIR and how to handle type analysis, activity analysis, and differential use analysis. But the issue with that is that MLIR currently lacks a mature alias analysis implementation. And we also want to optimize further for more AD-specific optimizations and, of course, test compile and runtime performance.
We also have some open questions that we are grappling with currently. For instance, and this is just a subset of them, can we expose an API that doesn't require all of this cruft around MLIR? can you use our system and extend it without being married to MLIR? Can you implement your adjoints using different languages like Julia or Rust? In addition, this design that we have for our interface is evolving, I would say. Can we infer information? Is the set of interfaces we have necessary and or sufficient? We would love any input from users or collaborators, anything of that kind. And with that, that is the end of our talk. Thank you for listening.
So, any questions?
So this is related to the second question with respect to sort of an interface design. So back when earlier Alex and I hacked together a quick and dirty forward mode, we had implemented a different interface, for the forward mode, create dual rather than the reverse mode create adjoint. There's other places in sort of like the Enzyme LLVM code base right now where using say table gen, we're able to write the sort of like generalized derivative for it, and it will create out of that, definition file the corresponding forward mode and reverse mode utilities. Do you think that there is a way to sort of design an interface, and perhaps this is only for a subset of operations that this is potentially workable with, where you just define some high-level properties and it generates for you both the forward and the reverse mode pieces?
Right. So the question was, well, there was a lot of context, and do we think that there is a way to define at a high level a much simpler interface and then generate a lot of the information that we need? Is that more or less? I would say yes, hopefully, and that would be a very promising direction to look into. I think just making this more user-friendly and accessible, it would be a huge win for everyone.
We have also tried to make it possible to just create in code the 3 functions that they are implementable, so that the barrier to entry is maybe a bit lower.
Other questions? Comments? All right.
So you mentioned that, with the existence of AD at both MLIR and LLVM, there's interesting comparisons to be done on, potential benefits from sort of different levels here. So there's the one direction where you could take MLIR and run it through the various lowering passes and then try to differentiate at the LLVM level. Simultaneously, inside of Polygase, there's raising, so you can take all the CFG style forms and try to find the SCF and affine sort of bits, and you can try to take LLVM and convert it to a high level MLIR. And then there's also somewhere in between, right, where you can imagine, say you autodiff some outermost routine, and then you defer some inner piece where you might differentiate the outermost loops, but leave the inner piece for some later perspective. I'm curious if you have thoughts or ideas in when particular operations would be best to be done in terms of what's best at the high level, what's best at the low level, and what might be good to sort of defer between.
So for the question was, there is this interesting trade-off at the level of abstraction. They heard? Okay.
I think the first thing is we probably will need to create infrastructure so that is actually possible, which will need to be some kind of annotation path. But I think that is possible. We were also already thinking about if we have passes, if we have parts of the code which we cannot differentiate, if we can just defer to LLVM enzyme and maybe cheat our way through some parts.
Yes, thank you. If there are no further questions, let's thank the speaker again.